Validity, satisfiability, and unsatisfiability are properties of individual sentences. In logical reasoning, we are not so much concerned with individual sentences as we are with the relationships between sentences. In particular, we would like to know, given some sentences, whether other sentences are or are not logical conclusions. This relative property is known as logical entailment. When we're speaking about propositional logic, we sometimes use the phrase propositional entailment. By definition, a set of sentences, delta, logically entails a sentence phi if and only if every truth assignment that satisfies delta also satisfies phi. In what follows, we will use this notation shown here, where we write delta, then what's called the double turnstile, a vertical bar followed by an equal sign, and phi as our way of notating the statement that a set of premises delta logically entails phi. As an example of this concept, we can say that the sentence P logically entails the sentence P or Q. Since the disjunction is true whenever one of its disjunctions is true, then P or Q must be true whenever P is true. On the other hand, the sentence P does not logically entail P and Q. The conjunction is true if and only if both of its conjuncts are true, and Q might be false. Of course, any set of sentences containing both P and Q must logically entail the single sentence P and Q. Note the relationship of logical entailment is a logical one. Even if the premises of a problem do not logically entail a conclusion, this does not mean that the conclusion is necessarily false. Even if the premises are true, it just means that it's possible that the conclusion is false. Note also that logical entailment is not the same as logical equivalence. The sentence P logically entails P or Q, but P or Q does not logically entail P. Logical entailment is not so much analogous with arithmetic equality as it is with arithmetic inequality. One way of determining whether or not a set of premises logically entails a possible conclusion is to check the truth table for the proposition constants in the language. This is called the truth table method. First, we form a truth table for the proposition constants and add a column for the premises and a column for the conclusion. We then evaluate the premises, we evaluate the conclusion, and we compare the results. If every row that satisfies the premises also satisfies the conclusion, then the premises logically entail the conclusion. Otherwise, they don't. As an example, let's use this method to show that P logically entails P or Q. We set up our truth table and add columns for our premises and the conclusion. In this case, the premise is just P, and so evaluation is straightforward. We just copy the first column. The conclusion is true if and only if P is true or Q is true. Finally, we notice that every row that satisfies the premise also satisfies the conclusion. Hence, P logically entails P or Q. Now let's do the same for the premise P and the conclusion P and Q. We set up our table as before and evaluate our premise. In this case, there's only one row that satisfies our conclusion. Finally, we notice that the assignment in the second row satisfies our premise but does not satisfy our conclusion. So logical entailment does not hold in this case. Finally, let's look at the problem of determining whether a set of premises consisting of the sentence P as well as the sentence Q logically entails the sentence P and Q. Here we set up our table as before, but this time we have two premises to satisfy. Only one truth assignment satisfies both premises, and this truth assignment also satisfies the conclusion. Hence, in this case, logical entailment does hold. As a final example, let's return to the love life of the fickle Mary. Here is a slightly simplified version of the problem from the course introduction. We know P implies Q, that is, if Mary loves Pat, then Mary loves Quincy. We know M implies P or R, that is, if it's Monday, then Mary loves Pat or Quincy. And let's say we know that it is Monday. Let's show that Mary loves Quincy. To make this determination, we form the truth table for our language. We evaluate each of our premises, and we evaluate our conclusion. Finally, we check that the conclusion is satisfied in every row that satisfies the premises. Hence, in this case, we can say that Mary loves Quincy is a logical conclusion from the premises. Note that logical entailment and satisfiability have an interesting relationship to each other. In particular, if a set of delta of sentences logically entails a sentence phi, then delta together with the negation of phi must be unsatisfiable. The reverse is also true. If delta and the negation of phi is unsatisfiable, then delta must logically entail phi. This is guaranteed by a meta-theorem called the unsatisfiability theorem, shown here, with a small proof that it's correct. An interesting consequence of this is that we can determine logical entailment simply by checking for unsatisfiability.